I'm going to look at another example involving linear modeling, and this one actually came up recently in a discussion, and it was height versus age of a person. And I guess the main question was, what is the limitation of the mathematical model that we came up with? And of course, there are limitations to this. But let's go through the example first. So the height of a person was measured at 130 centimeters when they were 8 years of age, and 152 centimeters when they turned 12. So part A, assuming the relationship is linear, find the equation relating height with age. And then part B, state one limitation of this model. Okay. Right, so I'm going to do this on another board because I've run out of space. Okay. Okay. So we need the equation, okay, that relates height with age. So I'm just going to do the solution here. Okay. So when the person is 8 years old, okay, what's their height? Okay. The height is 130 centimeters. So I'm writing down the data. Okay, this is what we know. When they turn 12, okay, their height is 152 centimeters. Okay. In fact, that's really all we need. How then do we find the equation or the linear equation that relates age and height together? All right. First of all, let's work out the gradient. Okay. So at 8 years of age, height's 130. Okay. This is the x. Okay. So we're relating height with respect to age. So this will be our x1, this will be our y1, this will be our x2, this will be our y2. Okay. I'm not going to graph this at the moment, but if you just wanted to see a quick diagram, it probably looks something like this. It's obviously I can't start from 0, okay, clearly, because especially of the heights, so the graph will be too big. But this will be your age. Okay, so let's call that A, and this will be our height H. Okay, so 8 years of age, maybe 130. So that's 130. Okay, and at 12, it's 152. Okay. Okay, I might just put a little break there. Okay, because the graph doesn't start from 0. It's a positive gradient, we can see that. All right, let's use the 2-point formula. M is equal to y2 minus y1 over x2 minus x1. Right. In other words, the difference in the y values over the difference in the x values. Difference in the x values, 12 minus 8, it's going to be 4. Okay, because we want the change in height per year. That's what the gradient represents. And what about the change in y? So it's going to be 152 minus 130. Okay. So 152 minus 130 is 22 over 4, which is equal to 11 over 2, or 5.5. So I'm actually, you know what, I might just put it in decimal. I'll express the gradient in decimal. So it's about 5.5. So what does this mean? This means that at least between the ages of 8 and 12, this person was growing at a rate of 5.5 centimeters per year. Okay, and that's what the gradient represents. Now what we need is the y-intercept, okay, to express this relationship correctly in the form y equals mx plus c. All right. So height is equal to 5.5, okay, times the age plus c. Okay, so that's our x value. All right. Remember what we call the x value when we're not using the letter x. Okay, we call this the independent variable. When we're not using the letter y and we're using some other pronumeral, we call it the dependent variable. Okay, so the independent variable here is age, a, and we can use one of the original points. We can use 8 and 130 substituted into the formula, and we can find our value for C. All right. So H is 130 is equal to 5.5 times the age 8 plus C. Okay. Okay, so that's should be equal to 44 plus C. Okay. Moving the 44 over, we'll just have a bit of space here. Okay, so 130 minus 44 equals C. Okay. And C is equal to 86. All right. So therefore the equation is, okay, that links height, or that links height with age in, I guess, in algebraic form, is height is equal to 5.5 times the age plus 86. Okay. So the next part is state one limitation of this model. And let's assume, for example, this person's age, let's try to predict this person's age when they're 30 years old. Okay, so at age 30, height is equal to 5.5 times 30 plus 86. Okay, we get 251. You can see that, so I'll just brighten that a bit. You get 251. It's pretty tall. Okay. Okay. So what this model assumes that the person keeps growing indefinitely. Okay. So, and also assumes, sorry, just before I flip the board over, this also assumes that when the person is born, their height is 86 centimeters. Okay. So to answer this question, okay, well, to continue answering the question, I'm continuing on from the last board because I've just run out of space. Okay, so at age 30, okay, height is equal to 5.5 times 30 plus 86 equals to 251. Okay, I might just put at age 0. All right, so this is from birth. Okay, their height is 5.5 times 0 plus 86, which is equal to 86 centimeters. Okay, so that's close to a meter. So clearly we have a limitation to this model. So this assumes that everyone is growing at exactly the same rate throughout their entire life. Okay, so one limitation is that the model assumes constant growth throughout the entire life. And this is not true. Okay, and it's constant growth as well. So people grow at different rates at different ages as well. So people grow at different rates at different points in their life as well. Okay, so again, comparing, for example, from 8 to 12 years of age, from 12 to 16, typically your growth rates are higher. Okay, so you might start off, for example, growing fairly at a fairly low rate, from, let's say, from 8 to 12, and then from 12 to 16, the rate of growth might increase, and then from 16 to 20, might start to slow down a little bit, and then from 20 to 25 slows down further, and then you may basically hit a point where that's it. You've reached the limit. The body says, that's it, I'm not growing anymore. I've reached the height that I'm meant to reach. Okay, so it's only linear at a certain point, or between certain ages, okay, or at a particular gradient. So there's clearly a limitation there.